Alright, this is the other homework problem I gave you. So we have this person on this little ride that spins around and around, and they don't slide because they're pinned to the wall and there's a friction force. Let's talk about a free body diagram. So we're going to have the static friction force. We're going to have the weight. For the static friction force, you know what, here's what I'm going to say. I'm going to actually label this a little bit more carefully. So I have the static friction force on the rider due to the wall. I have the weight of the rider due to the earth, and I have the normal force on the rider due to the wall. So let's set up our equations. First, I know that the friction force on the rider due to the wall balances the weight, which is her mass times g. The next thing is, I also know that the normal force is what's making the rider accelerate in a circle. So nm equals v squared over r. Now, I have a third equation that's useful that relates friction and normal force. I should put rider and wall. Friction is mu times the normal force. And I have a mu static here. So just to be clear, okay, we want to know the minimum speed of the rider. So let's just throw a couple things in here. I know that this is mg. I know that this is mu static times mv squared over r. And I want to isolate v. So the m cancels. So I'm going to have rg over mu s under a square root gives me v. And I'll let you plug in the numbers and solve that. So if I want to go ahead now and get they call it the centripetal force. What that means is just the normal force that's producing centripetal acceleration. That's going to be, so for part B, the normal force is what's producing that centripetal acceleration. That's going to be mv squared over r, which is going to be m times rg over mu s, since that's v squared, divided by r. The r cancels, and so I'm getting mg over mu s is my normal force. I'll let you go ahead and plug in numbers.